the magnetic field intensity. And last time we just started to discuss, actually over a couple of sessions, we were discussing on the behavior of magnetic field in material media. So, and one thing which was very, very important, it was that the materials, they can be considered as ferromagnetic, where they can become very good magnets, paramagnetic and diamagnetic. And these, what is interesting, what is important into distinguishing which one is which, it is important to notice that if we look at the Mendeleev table, the metals, they are somewhere in the, when I say somewhere, the metals, you can find them on the left side of the table. So you look at the Mendeleev tables, those are the metals, okay? You find them there. And these metals, if they have odd number of electrons, so if they have unpaired electrons, when we put them in different, in the course of chemistry, and it's also important even for us with regard to the behavior of materials when they are put, when in interaction with the magnetic field. It matters a lot whether we have a single electron at the outermost shell or a paired electron. So if we have single electrons, the material, it will be paramagnetic. If we have pairs of electrons, then we have diamagnetic, because the paramagnetism, which, I mean, this is how they can be classified. And then there is the only difference that is between these two is that the relative permeability, it changes a small epsilon with respect to 1, okay? So they can be, it's very close to 1, but it can be either much smaller. For example, diamagnetics, they have a relative permeability slightly smaller than 1, and the paramagnetics, they have a permeability slightly larger than 1. So this was something that we mentioned the last time. And in the materials, we also learned that we can, magnetization can be developed inside the material. If that is the case, then we can write the relationships between the magnetic flux and the magnetic field intensity. And regarding those, if you want to write a short review, we can say that the H, the intensity, is equal to the magnetic field flux divided by the permeability minus the magnetization. And the magnetization, this is the dipole moment, the magnetic moment's density. Magnetic moment's density is this magnetization term that we see here. And from here, we know this, we can also say that if we consider that this magnetization, it is related to the, if we write this one, how it is related with the currents, we can also, later, then we wrote last time the following expression. We said that this is B over mu 0 minus M, this was equal to J, and finally, this is the H, which is reported above. So here we have the J cross H. This is equal to J, but this is now J free. The free, the electrons which come from connecting a piece of metal to a battery. So if you have a piece of metal, you connect it to a battery, and it has a resistance, and you have current flowing, we're talking about this, okay? Then the induced currents, because of the magnetization of the materials, now they are found inside this H, okay? So, and then from here, we can use the Stokes theorem. So here we have Stokes theorem. And this, from the Stokes theorem, we can integrate this over a surface area. And finally, so we get this, the curl of H ds, this will be equal to H dl, okay? And this crosses the curl of H, this is equal to the J free, and this J free integral with ds, this is equal to the current. So this is the total current, because the JF it's ampere per meter square. The surface, this is measured in meters square. So overall, we get current, I, which is measured in ampere. So overall, we see that from the Stokes theorem, from this relationship here, using Stokes theorem, we find out that this is equal to this. We have seen an expression similar to this one, which used to be something like the line integral of BDL. Some of you might, you should remember this one. This was equal to mu0 I. Okay? So we had this before. Now we have this expression regarding the H, and this mu0 is missing in this expression here. Now let's assume for a moment. Let's see. We're going to see a couple of examples, and in these examples, let's assume that we have a cylinder, and this cylinder, this has a magnetization, which is written like M. This is equal to M times AZ. Okay, which means that if this is a cylinder, we assume that this is the Z coordinate system, and this would be the magnetization. In fact, do you remember? If you remember, we solved an example which was similar to this one, where the cylinder, it was limited. Okay, and we asked what was the magnetic field here at some point here on top. Now this problem is changed slightly. We assume that this cylinder is infinitely long. Okay, it's not limited. We cannot assign a clear length L, so we cannot do this one now. So if you check, if you go over your notes, this example is going to be slightly different. And now, so if we assume that this is infinitely long, if this is the case, then it looks like we can find the magnetic field only as a function of radius r. Okay, which means that we can find it with respect to the distance to the axis of the cylinder. So here we have B is equal to BR, or we need to find it as a function of this. What is the first thing that we do given the magnetization? So any comments? We are given the magnetization, and we want to find the B. Come on, we need to find the current because of the magnetization over the volume. Okay, and then we need to identify what is the current density because of the magnetization, but on the surface. Okay? So these are two quantities that we need to identify right away. And the first one, this one, is equal to the curl of the magnetization. And the second part, this is going to be magnetization cross product with AN, where AN is the normal vector to the surface area. So in this case, what is the AN for this shape or for this configuration that we have here? What is AN? Thank you very much. It's the AR, that's correct. So we have here the AR. This is the only one that we have. If this was limited, probably we could have considered a couple of here, like minus AZ or plus AZ. This is just to make a link with what we talked the last session. Okay, but now these are gone. Okay, so that we are not confused, let's do it like this. So only we have the AR, that's good. But now, what is the J because of the magnetization over the volume? We have to consider the space derivative of the magnetization. Now, what is this? So in cylindrical coordinate systems, we have to figure out what is. So can you give an answer right away?
Sa është zero me që është uniforme kështu për gjatë gjithë të cilindrit.
That's correct. And we know that whenever we find a current, so I'm going to write something which I'm going to erase it very soon, but assume for a moment that what are our coordinate systems? This is cylindrical. So we have R, phi, Z. Okay? The first thing that we have to remember is this. Good. The second thing is to identify H1, H2, and H3, which are the metric parameters which convert the angles into units of meters. And these are going to be like what H1 is 1, because this is already measured in meters, this one. The phi, the other one, it's measured in radians, so this needs an R here, and the Z is also 1. Then, what we do next is that to calculate the curl, we put here AR, A phi, and AZ, and here we have the derivative with respect to R, the derivative with respect to phi, and the derivative with respect to Z. And here we put MR. What is MR here?
It's 0 along MR.
It's 0, that's correct. So here we have MR times AR plus M phi times A phi, okay, plus MZ times AZ. So this is the M. But now, so this is the general expression of M, right? So it looks like MR is equal to 0. You are right. M phi is also equal to 0.
That's 0, yeah.
And the AZ, this is M, just constant. Now, this is a constant, but any derivative here of a constant value would end up in 0. Okay, so you are correct. This is going to be 0. But now, that's true, it's 0. But let's have a look of how the curve really looks like. So the curve is going to look something like this. Let's write this for a moment. This is AR times 1 over R, the derivative of AZ with respect to phi, minus derivative of A phi with respect to Z, plus A phi, the derivative of AR with respect to Z, minus the derivative of AZ with respect to R, plus, right now, I'm looking at this expression on the paper. We can always, these expressions, we can always derive, okay? If you remember a few sessions ago, we used to derive these, and with derivation, I mean this, that always, when we had the curve, we had this permutation relationship between all the components, okay? So we were able to write this whole expression as a single term, but we had to calculate all the permutation between R, phi, and Z. So this one, we can always derive this, but probably takes too much time to derive this continuously. So you can take this from the formula sheet if you are asked in a test or in an exam. And it's always good to derive this at least once, okay? And here we have R times A phi minus the derivative of AR with respect to phi, okay? And this is, we multiply here again by 1 over R. So this expression is going to look like this. Now this A, in fact, should be the M, okay? But let's leave it like that. You are right, this J, this is equal to 0. And then we have to figure out what is this current density on the surface. And in order, this was something that we needed to erase it right away. But then the current, because of the magnetization on the surface, now the magnetization, let's remember that it looks like this. And a magnetization which points like this, times AR, cross AR, So the J, and also we can assume that like this, R, phi, Z. We know that if we do the cross product in the direction of the clockwise, in the direction of the arms of the clock, we get a plus, which means that AR cross A phi, this is equal to AZ. Okay? And then let's see what we have. Here we have that M, it is AZ. So here we have AZ cross AR. This is the J. Okay, what is this AZ cross AR? We are going clockwise, which means that this is going to be plus A phi. Okay, so this is just regarding the direction of the current density. So here it looks like the J, the current density, because all the magnetization on the surface, this is going to be equal to M AZ, this whole magnetization cross AR, the magnitude is going to be M, and the cross product AZ AR is A phi. So it looks like the magnetization is going to be a current which flows like this, a surface density which flows like this. And we need to find the magnetic field around, and in order to find this, we need to use the relationship where we either use this or we use this HDL, this is equal to I, okay? So this can be the two expressions that we can identify, and in order to do this, we need to define a closed loop in this, close to this construct. And this closed loop, we can draw something like this. Of course, this doesn't have to be so huge, but we're just drawing it this way. And in this case, we assume that this is BDL, and the BDL, this is going to be equal to, so first of all, it's good also to identify what is the direction of the magnetic field. So if the current is flowing this way, it looks like, according to the right-hand rule, the B is going to point upwards. Okay, and then if we assume that this has a length L here, we can think that B times L, this is going to be equal to μ0 times I. Now here we have the question, what is the current that is passing through this complete loop? Now, through this complete loop, this is a problem which can be considered as equivalent to the solenoid. A solenoid, it's a construct which looks like this, okay? And a construct that looks like this, the magnetic field that we find inside the solenoid, it's always equal to the BDL, again similarly, or B times L, and this is equal to μ0 I, and I is the number of times that the wire goes, intersects this area, and we multiply it by n, okay? So this is a problem which is similar to that. And in this case, this B times L, this is going to be equal to μ0 I, and in this case, the I can be written as J times L. Okay, and the current density, this is a question. So this, if we had Jm in the volume, what would you expect the unit to be for the current density if the current is flowing through a volume? This is the unit, okay, it's ampere per meter square, but the current density over surface areas, so J because of the magnetization on the surfaces, the unit is ampere per meter, okay? So we have to check also the units. So if we check here, it looks like the J is ampere per meter times meter. So we get here the current term that we are looking for. So that's all we need to include here. And we may have to include also these edges. Okay, but here the BDL is going to be equal to 0 because B is pointing upwards and DL is 90 degrees. And we know that the dot product when the angle is 90, it will end up being 0. So finally, it looks like the magnetic field is going to be equal to mu 0 J. So this is the magnetic field which is going to be measured in our system. So the link that we make here is the following. We have a magnetization. The magnetization induces a current density J, which in principle, this is effectively this. It's a current, okay? But it's a current density. And from this current density, we can find the B. So this is how we may need to think in this for such problems. Now, what we can do here, so the answer finally is the one which is shown there. Now, let's assume for a moment if the magnetization was not a constant. So allow me to erase some parts here. Let's assume that the magnetization, it can be written as K R squared times A phi. Okay, so it looks like where R, the little r, is the distance from this axis. So this is the little r, and let's assume that the r, it changes from 0 to a capital R. So let's assume that the maximum thickness, not maximum thickness, the maximum radius is capital R. And now, let's go back for a moment and let's write this one in this way. This is going to be equal to MR okay, plus M phi A phi plus MZ AZ, right? So this is the M vector. Before a moment, these were not here. We just had a constant value here for MZ, okay? Now, it looks like we have non-zero. So this term that we see here, this is this M phi, okay? So the only magnetization is this term, and for sure it looks like that MR and MZ, they are both equal to 0. Probably we can write them. So this is 0, and this is 0 again. And the same question starts again. So given this magnetism, the question is the same. So given the system, identify the magnetic field that exists for this configuration. So I hope you're seeing this clearly, what the magnetization is. And we follow the same steps. The first step is we try to identify the current density in the volume. So the current density because all the magnetization in the volume. And we have the same coordinate system, is cylindrical. And we have this expression that you see here. But then we move on and we see what is AZ, what is the Z component? The Z component, it is 0. So this AZ, this is 0. We have the A phi. Instead of A phi, we can write KR squared. Okay? So this is equal to KR squared. What is AR? This is also 0. Probably, maybe I can substitute them like this. AR. This AR is 0. This is 0. AZ. What is AZ? This is also 0. What is A phi? So here we have R times A phi. R times A phi, the A phi, it's KR squared. This is the KR squared, but there was an R already before. And what is the AR? AR is the zero here. So now let's have a look. And I just erased, but the unit of the current density that we may expect in this case, it should be ampere per meter squared. So the unit of this quantity should be A over meter squared. So let's try to get the final answer. And here we have the derivative of the zero with respect to phi. This is 0. What is the derivative of kr squared with respect to z? We do not have an explicit relationship of this term with respect to z, okay? So this is also 0. And here we have the derivative of zeros. They are constants, and they are also 0. The derivative here, this is 0. So it looks like we are left with a single term, which is going to be equal to a result in the AZ direction. And we have here KR cubed. So here we get, this is KR cubed. If this is KR cubed, then the derivative of KR cubed with respect to R, what is this? What is the derivative of KR cubed with respect to R? This is going to be 3KR squared. This is the derivative of the term times 1 over R times 1 over R, because this was a term which is in the curl operator in cylindrical coordinate system. So finally, it looks like this is going to be 3KR. 3KR AZ. Okay? So apparently, maybe it's best if we draw this one a little better, or once again. And these don't have too much information for the moment. So let's draw this again. It looks like we have our cylinder like this, and the current is 3KRZ. So here in the center, the current is what? What is the current right in the center here? It's 0, because R is 0, and R is the distance from the axis. So this is R, okay? So it looks like here in the center, there is no current flowing, okay, up. But then here, we have this current, and then if we get a little further, and this is current density, okay, this is a little larger. So it is a linear increase, because this is linear with R. So if we draw a graph of the J as a function of R, assuming that this is the R, like X, Y versus X dependency, we can have something like this. So if we get further and further, the current density is a little larger, but this is all in the volume. Okay? Similarly, this goes like this. We go here, 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 and here. Okay, so it looks like there is a flow which flows out in this direction, and this is just the JMV. Now we have to look if we have, what is the JMS? What is the current density on the surface area? So the current density, we have to calculate a similar expression. So we take the M cross AN, and the M cross AN, let's see what we have here. So M itself, it's KR squared, so we have here JMS, the current density, because of the magnetization on the surface with a unit which is measured with amps per meter. This is going to be equal to KR squared, we're getting this from here, times A phi. No, sorry. Yeah, I think I said something verbally which was not correct, so I can repeat it from the beginning. The current density is equal to the magnetization. Yeah, I think this is, I said it right. Cross AN. Again, AN is going to be the AR. Okay? It's going to be such a vector. Cross AR. Now, what is A phi cross AR? Let's do a similar sketch because it's good to not memorize anything. Okay. If you have good memory, of course, it's highly valuable. So we have R, phi, and the Z. So if we go clockwise, when we do cross product, we get a plus sign. So here we have A phi cross AR. What is A phi cross AR? It's going this way. So we're going counterclockwise. So since we're going counterclockwise, the result of A phi cross AR, this is going to be minus AZ. Okay, so the result will always be the third one, but the direction clockwise versus counterclockwise, it matters. Similarly, let's say AR cross AZ is going to be equal minus A phi. But for now, we care about this. So the second example is if we are doing, so what did I do here? I said AR cross AZ. So we're talking about this is counterclockwise, the result is going to be A phi, but with a negative sign. So it looks like this is going to be equal to minus AZ K R squared. So let's try to draw this column on the board. So it looks like we have a system that because of this configuration of the magnetization, we have a current which flows into the volume upwards, but then it flows over the surface downward. Okay, so this will be the current on the surface. So these currents, since they belong to the volume, the current will flow down. So if this has some n, it looks like the current, it might circulate into the volume upwards, it comes downwards, and maybe it comes, it forms like a structure or like a construct like this. Now, if someone asks what is the surface, what is the thickness of the surface, you might assume something in the order of a micrometer. Okay? That's the surface, that's how thin it is. So it should be infinitesimally thin, but for sure it's not going to be one layer of material. And since this is a metal, we can assume that the distance between two atoms is not zero. This is 10 to the power minus 10 angstrom, or meters. So if this is 10 to the power minus 10, you don't have a layer of two atoms, maybe something in the order of 10 to the power 1 to 10 to the power 2. That makes a surface layer. So it looks like whatever the radius is, we have current flowing outwards, and then in the outer shell, we are going to have just here, in the thickness of around a few micrometers, we can have a current which is spilling out, like going up and spilling out down like this. Now the question is one thing that we can immediately ask is the following: is the current conserved? Or, which means that is the current that flows upward equal to the current that is flowing downward? Okay, it could be equal, it may not. So we can check that. Okay, we can check what these values would be. So how do we find? Let's try to find out actually what is the current flowing outwards. The current flowing outwards is going to be equal to current is equal to the integral of current density J dot ds. So how can we find this value? Or can anyone suggest any way to integrate this one correctly? We need to find an infinitesimally small area element. So I said that if we are looking at the cross section section of this wire like this, it looks like we are going to have currents which are flowing down into the board in the top, and also we're going to have currents which are coming out of the board like this. Okay? And now the question is how we are going to integrate. Since the symmetry of the current is kr squared, it looks like what are the points where this J is going to be constant. So the symmetry is cylindrical. So one can say that we also do this here. So we said here that if we get this far away from the center and this far away from the other side, we get that the current density is the same. So these vectors should be equal probably, these two that I'm showing here. So this means that at this point here and here, the current density is the same because the radius is constant. And then we can assume also, that this infinitesimally small area, the current density is also the same. The question is, what is the area of this segment that we draw here? For any radius r with a thickness of dr, the ds is going to be equal to 2 pi r dr. Okay? So we can cut this one, and we can stretch out all this wire that we see, and the surface area of that one is going to be equal to the length, which is going to be 2 pi r, times the thickness, which is delta r. Okay, so this is delta r, and this is a 2 pi r. So then we come to this expression, and we have to integrate the J, which is equal to what? So this is the J, is 3kr, where k is a constant. Let me denote here. K is a constant. Let me see for a moment, magnetization. So, I want you to think for 5 minutes, what is the unit of K? Okay, and I want to answer you approximately in 5 minutes. And meanwhile, I just want to ask you once again that if it's possible for the attendance, you should enter the attendance. I see that some of you have entered the attendance pressing once in the comment section of the lecture, but you have to answer so that you don't see the answers of each other. You have to answer at the Google Classroom.
Professor,
yeah.
Aty nuk mua më del që nuk mund të shkruaj aty si video të edit.
Then maybe I could not do it in a short time because I did it during the class when I already started. Can you enter comments, private comments? I think you have the option. Okay.
Okay.
You go to the last notification that I put in the Google Classroom, and you add some private comments. Okay. And I'm expecting to see some amazing list of text of books. Okay. So for anyone.
Shikoj njerë, del përgjigja ime aty.
Prita shikoj pak. Përgjigja jote ku dha përgjigja?
Te Classroom, kam shkruar kështu si në Paint, një gjë e këtilla tjetër ajo.
Okay, I'll have a look later, not now. Do shikoj pak më vonë, mirë. Pra, kush u fut në klasë pak më vonesë, shikoj që te Google Classroom shkruani librin e fundit që keni lexuar. Shpresoj mos jetë libri Gaçi Bushakës, po. Okay, so let's move on. So here we have the J. The J is 3kr, and again the question stands. Please, in 5 minutes, provide an answer with what is the unit of K based on these quantities that you are shown here on the board. Okay? You should be able to find it. Maybe it has no unit. Maybe it's just a factor. But let's move on. We have here 3kr. AZ dot product with ds. Now these two are vectors, okay? So what is ds? ds, this is going to be equal, this is AZ, because ds, the surface area is always defined by a vector which is perpendicular to that surface area. So probably you might agree that this is 2 pi r dr AZ. Then this is going to be equal to, so AZ, dot AZ is equal to 1. So we don't end up with 0 or something. And this is a constant, 3 is a constant, K is a constant, R is not a constant. So this 3K and this 2 pi, we can take them out. So it looks like we get 6K pi. 6K pi integral of what we are left. We're left with R squared dr. R squared dr, the limit of the integral is from 0 to R. And then here we get the integral is R cubed over 3. So we get here 2K pi R cubed. Okay? So this is the current, the total current that is flowing upwards. Probably now you have a huge hint on the unit of K. So you can look at this expression, and apparently you can also find the unit of K by looking at this expression. Okay? So you get the unit of M, divide by meter squared, you get this, but probably here you get a better hint. So this is the current which is flowing upwards. The question is now, what would be the current which is flowing downwards, which is spilling out over the outer edges of this cylinder. So the total current on the surface is going to be equal to the current density on the surface, which has units of ampere per meter, times the length. With what do we need to multiply this term? So we are looking to find out, so let's say that we put here an ammeter, okay? So let's assume that we cut this like this. Or let's cut a little more. So we cut this like this. We connect this whole thing with a wire. We put this into an ammeter, okay? And we put this back to the same cylinder. What are you going to measure here through this ammeter? So in order to measure the current, you cut it somewhere, pass the current through, find out what it is. So what is that current? This is Js times a length, which in this case is going to be equal to 2 pi r. And it is the capital R, because this current is right at the edge where we have the capital R. So what is Js? Js is kr squared. So this is equal to kr squared times 2 pi r. And in fact, probably we did a mistake here. It's not a real mistake actually, but we should know that this r here is r squared. Because, so even here, assuming that this is on the surface, it's better if we write this one, this is k r squared. And so that we are not confused, this is what we got before a while, and this is what we are getting now. This is 2k, so we have also a minus sign, because this minus sign is still there. So we get minus 2k pi r cubed. So this is the current flowing, spilling out over the outer surface area. It's minus 2k pi r cubed. And the current which is flowing upwards is equal to this. So it looks like if we add these two, we get the total current of 0, which also means that the current is conserved. So the current flowing upwards is coming down backwards. So, okay, good. So far, what we did was that we had the M. We found the current density on the volume. We found also the current density on the surface. And we figured out that this is 0. Now, probably we may not need this one anymore, so I'm taking this away. But it looks like with this new information, if the total current in this system is equal to 0, so we have an internal current flow in the system. But it looks like if we are an observer from here, we are seeing a system where the current is 0. So if you want to measure the current here, that's what it is. So what would be the magnetic field at a point like this. So we have. So if we construct such a system, we can always say B time B dot BDL. This is equal to mu 0 I. Okay. But now this DL is so we know what DL is, but this current I, this is 0, because the current which is flowing in this whole system, the net current is 0, because we show this in here, the IS and the I volume. Let's call this one I volume. And this quantity, this is measured in amperes, and this is also ampere. So this means that the B of R is equal for, this is the B for R larger than R. This is equal to 0. Okay. But now we need to find also what is the B inside this volume here. So probably at some point around here. In order to do this, we write the same expression. We say BDL. This is equal to mu 0 I. But the question is the following: what is I? The I, it can be found in the same expression, only that we are not going to integrate from 0 to R as we did before a while, because we don't need the whole current, but we need the current up to some R prime. Let's write this one R prime to distinguish it from these R's, because we might get confused. And then the final answer we can get for the current is that if we integrate this up to R prime, the final answer is going to be something like 2k pi R cubed. Okay, and this is equal also to, let's write this side of this left side identity. Let's write this one to the right side here. It's going to be B times 2 pi R. That's good, so it looks like a 2 here, it can cancel out. We have also a couple of pi's to cancel out. And this R, we get an R squared here. So the magnetic field, it looks like it's going to be equal to, so we're left with nothing on this side, 2 pi R. So everything, all the terms are left, it's mu 0 times k R squared. But we need also a direction. What do you think the direction is going to be? Okay, so this is the, let me think for a moment, it's mu 0 KR squared. Yes, that's correct. And at the same time, we can also have a look at this. The KR squared as a magnitude, as a quantity, it's equal to the magnetization. So if you look at, if you go back for a moment and see what was given initially, this magnetization, we can also write it like this. So this is mu 0 times L. Okay, so this is the end of this other example or exercise. Any question so far? I have a couple of comments.
Besoni që kemi marrë kështu disa shembuj, pak a shumë si ky me cilindër, por edhe të tjerë. Edhe nuk e di unë për vete kam arritur në pikën që nuk di cilën formulë të përdor për gjetjen qoftë për B-n apo për I-n. Apo nga që janë marrë shumë formula dhe nuk e di si dallon kështu me raste. Apo kush përdor, se për shembull këtë integralin e B-dl si është barabartë me mu 0i, këtë kemi marrë në fillim. Më vonë morëm Biosavartin, që ai kishte goxha shembuj kështu, me qoftë me cilindër, qoftë me që
Okay.
mund të puna është se mund për vetë më thonë tani në këtë moment nuk është se di cilën të përdor. Mund të kuptoj këtë që bët ju, po vetë nuk e se më shkon mendja.
Yes. If what is the source of the electric field? The source of the electric field is a charge. That's right. It is a charge. Okay? So if it is a charge, and if the system has some symmetry, so probably I can erase some good parts over here. Probably I can start from here. So I'm going back to the charge to draw some similarities. Okay, so let's assume that we have a point charge Q. And what is the potential? We say that V is KQ over R. Okay, then if we have more charges, okay, which go like this, and probably this is like a wire, okay, a wire of length L. And we want to find the potential somewhere here. How do we solve this problem? We have to integrate here. Okay, so what do? We say that the infinitesimally small potential dV is going to be equal to K dQ over R. Okay, and then how do we construct this dQ? This problem. This dQ is always equal to what is the language that we memorize right away? We say that the following: at the height Z, we select an infinitesimally small element dz. Okay, this is how we always construct this problem. But let me do this better like here. We say at the height z, we select an infinitesimally small element dz, and then we find out where this point is. Then we write this expression: dv is equal to k dq over r. So we are using, this is the potential of a point charge. And this is the potential if we have a distribution of charges. But now, if this wire, this becomes an infinitely long wire, here we can use the Gauss Law. Okay? In Gauss Law, we do the following now. We say, what was it? I forget it. It's something like EDS, this is equal to Q enclosed over epsilon 0. And this was the integral over some closed area. Okay, so here we use the integral. Now, similarly, in magnetic fields, let me erase this part, hoping that we wrote it. In magnetic field, let's see how we are going to select the... So we said that in electrostatics, the source, it was a charge. In magnetic field, the source is a current. So before we had Q was providing potential at E. Now we have current, which is going to provide magnetic field. Let's call it like this. So this provides also the A, magnetic field vector. Now, if the problem is limited, so if we have a wire which comes like this, and it flows like this, and it comes backwards through a circuit, and if this current density, current flowing, so we have I. Here we draw I here, I again. So if this is limited in space, here we need to use the Biot-Savart law, because the potential, the magnetic field here, and here is going to be different. So in this case, we use the Biot-Savart law. In this case, we use this, similar to what we did here. Okay? So we are going to integrate. So what would this R be? So let's write this down for a moment. dV would be equal to constant K times gamma times dz over R. What is this R? First, let's figure out. We need to know what is this distance. You say a number. Probably this is distance A. And the distance of this wire, which is shown here, a limited wire, this is a distance B from the zero. Okay, so we assume that the zero is here. But this wire, it starts like here, and it ends like here, and probably it has a length L. Okay. So we're not doing something very tricky so far. We just need to write the distance R from this reference element to here. So what is the distance? Let's see. This is A from here, and this is a constant B plus Z. So R is equal to square root of A squared, we use the Pythagorean theorem, plus B plus Z all squared. Okay? So we put this expression here for R. A squared plus B plus Z over Z squared. Now dz is here. The integral, it should be from where to where? The integral is going to be from the beginning, which is B, up to B plus L. Okay? So the integral is going to be B up to B plus L. I hope this is clear. Similarly, when we come here, we use the Biot-Savart law because this is limited. And the Biot-Savart law will be the following. We say dB is equal to mu 0 I over 4 pi integral of dl over r squared. Now we have cross AR, right? When such a thing. So now here we need to integrate. So that's because we have limited in space. But the moment the current sources are infinitely long, then we have to apply. We can apply something which is similar to the Gauss law. So Gauss law is very useful and it is very easy to use, okay? Because you cancel out a lot of terms, or it's relatively simplified. So now imagine for a moment that we have this wire and we are going to use this term. And what is important for us in this case? We do the same thing. Let's assume that we have this point. What is the language that we have to memorize is the following. At the height z, we select an infinitesimally small dz. Okay? This is the only way that we can integrate over some quantities. Now this dz is this dl. So we identified it, it's right there. The next thing to identify is what is r. We need to find what is 1 over r squared. We look at the geometry that we are given. Probably we are given this distance a, and how far away is this point from here. So let's say this is also a height b. Then 1 over r squared of any general point here to here. We use the Pythagorean theorem, again the same. So in this case, the r itself is going to be equal to the square root of what? A squared plus, so this is here. What is the other element? We are assuming this is 0. This point where the current element is, it's at the height z. Okay? And this point, with respect to the 0, it's a height b. So this is the point P where we want to find the magnetic field. Okay? So how is this distance? It is this square plus this square. Okay? Which means that this is z minus b squared. Since we're looking for 1 over r squared, this is going to be equal to 1 over a squared plus z minus b all squared. We substitute this term here, then we will need to integrate for let's say, z is going to change from z to l, if the length is l, from z to l, from 0 to l. So this is Biot-Savart, this is the charge distribution, calculating the potential as a function of the charge distribution. Now, since these are limited, we use this. If the charge, the current density, or the currents, they go from an infinite length, then we can use the other laws, which is which are these. EDL, this is going to be equal to mu 0 r. Okay. We have a couple of simplifications, which we get them from integrating. So, with regard to this one, I want to remind you that here in this class, we integrated together. If we had a current here, we asked what was the magnetic field at some point here, right? And then, for a special case, by bringing this point down here in the center, I think we found that the magnetic field, this was equal to something like 2 pi 0 mu 0 I over 2 pi r or something. pi? 2 pi r, or 2 over r. I do not remember if we have this pi here. Okay? 2r. I think we don't have the pi, but you can correct me on this. If we derive this one from scratch, we can always get the correct expression. But I think from a general expression, I mean, we get these types of simplifications after we have applied the Biot-Savart law at some point like this. But now, maybe it's best, not best, but if you find any example in the textbook somewhere else, then we can start discussing, okay, for this configuration, to use the Biot-Savart law or not. That was the idea. So this cylinder, since this one is going from minus infinity to plus infinity, we cannot use Biot-Savart law, okay? Because depending also what we want to find, but it looks like we can make use of symmetries here, because for example, we don't have here the surface areas or the endpoints. But I guess if we have any question, we can immediately discuss it together and try to figure out what we're going to use. Okay, so we can move on to a couple of other examples. I think we have to move with to discuss the boundary conditions. And the boundary conditions, we did not cover them completely last time, but we just gave the general idea where we argued that the flux, it was a more essential quantity than intensity. Just give me a second. So, kemi mësim tjetër sot? Pas nesh?
Kemi me profesor Jolin.
Në 10:30. Në 10:30 keni? Okay, mirë. Okay, so now regarding the boundary conditions, we said last time that we can have medium 1, medium 2, and then we mentioned something. We said that the flux, it was more fundamental than intensity. Okay, and this is the same for electric fields and for magnetic fields. And the best example probably is the one that we can give here. So for electric fields, if you have a series of different materials, okay, so here you can have, this can be a vacuum, this can be a piece of glass, this can be a piece of, I don't know, a different type of plastic, this can be a rubber. So if we have a field which is flowing in this direction, we have 1, 2, 3, 4. We have 4 different mediums. One quantity which is going to be constant is the following. We have P0 is equal to P1 is equal to P2 is equal to P3. Okay? Because this is a flux, and flux it's equivalent to the number of field lines. Imagine for a moment that we have a charge here, and this charge, it has 10 field lines which point out like this, okay? But they go in straight lines. So what will be the flux of this other surface area? So what we are asking is, how many field lines are going to intersect this one? Well, it's the same. Then you come up here and see how many field lines are going to intersect here. It's still the same. Okay, so anything which is equivalent to a flux is more essential. And immediately, this means that the B is more, actually when you say essential, we have to pick up the correct word. It's a more fundamental quantity because it carries the word flux. But here, I can also construct in 10 or 15 minutes, I can also construct another argument which states that for many applications to find the currents, most of the time, it is best to use this because when we had this HDL, this was equal always to the current, to the free current. And always having a quantity which has all the other effects inside it is best. So for boundary conditions, actually this is better. But when you apply this one, using this one, it's better. So I can also construct a counter argument, but it's good for a couple of applications. But with this argument, this means that a field that is going to come down like this, and is going to go from medium 1 to medium 2, which now we can denote this mu1 and mu2, which is being the permeability, and the permeability, it can be written as mu1, it can be written as relative permeability R1 times mu0, and mu2, it can be written as relative permeability R2 times mu0. Now, what can you say if a material has a relative permeability of 1? What is this? What is this material? Any possible answer? So this material, if mu r is equal to 1, that means that the permeability is equal to mu0, which makes this one non-magnetic. So this makes this non-magnetic, and then so this is the first expression that we can write down, but actually writing this down is not. We have to derive this for sure each time, and the derivation is done by using laws like this. So we have here HDL. This is always equal to. We don't have a. So this HDL, this is equal to the current I. And in order to construct this, we assume 4 points, or we assume a closed loop. So we have points A, B, C, D, with a length L and with a width W. And if we do this one, we see that also the direction. Since this is a dot product, and this is DL, we have to consider only this component of the magnetic field intensity H. So in this case, we can have the H1 So this is the HDL, and this is all going to be equal to the current I. And this is actually here, this is the special case. So this is a special case when two mediums meet, when there is no current density. So often it might happen that whenever we have two different materials that they meet, there can be a small non-zero current which is flowing between the two materials. And this would be very, very amazing. But it's not always the case. We might have some currents which are flowing here, and we have to consider those. And regarding this, we state that the final boundary condition, we can derive both sides by L, and we find that H1 tangent minus H2 tangent, this is going to be equal to the current density Js. Okay, so this is the, and in the limit of So in the limit on the current density on the surface, which is going to be, for example, right here, we can have some currents which are flowing in this medium. It's like this barrier between medium 1 and medium 2 is like extending like this. If this is 0, we get these expressions. So this is the relationship that we can construct in here for the boundary conditions. Let's assume that we have a separation between two different planes that looks like this. So we have an incident wave, where magnetic wave, and we have this change of the angles. And then we have to look at the boundary condition, where the first one the discontinuity between the two different mediums, we can also denote it like this. So we can prove if the nu1 and nu2 are different in their magnetic properties. The discontinuity of this magnetic field intensity, it can be expressed like this. So we can use these two terms. And then if we use here the angles, we can write down in this case as H1 tangent is equal to H2 tangent. We are using this expression because we have the J is equal to 0. And then the other expression is going to be the mu1, H1 normal is equal to mu2, H2 normal. Now, the H1 tangent, let's see what is the tangent component. The tangent component is this one, and this is, how does this relate with the angle alpha? We know that sine alpha is equal to what? The opposite side, which is the H tangent, H1 tangent, divided by H1, okay? Which means that H1 tangent is equal to H1 sine alpha, H1 sine alpha. This is equal to alpha 1, and this is equal to H2 sine alpha 2. Okay, we get this one from this expression, and then the second expression, we have H1 normal. H1 normal is this component and this component. Okay, and this H1, this corresponds also to this side. We know that the cosine alpha, this is equal to H1 normal over H1. So then when we come here, we can write them as mu1 H1 cosine alpha 1 is equal to mu2 cosine alpha 2. So from this set of equations, we get this other one, and then what we can do then is we can divide both sides of the equation simply like this, and these will be cancelled. We have forgotten here an H2. So these will be cancelled out, and it looks like the tangent of alpha 1 over mu1 is equal to tangent of alpha 2 over mu2. So this can be, if you check carefully, this is really equivalent to the Snell's law. Okay, so whatever Snell's law in optics that are valid, this is also equivalent to that. Okay, so this is something on the boundary conditions that we have between two different medium. Now, I want to, at this point, so far, do you have any question? I just want to check some settings here. Okay, so if you don't have any question, before solving any example, I want to go over another an important aspect which you have, for sure you have seen this before. I want to talk about the inductance. So inductance. Now, let's assume for a moment that we have a wire or a circuit. So let's assume you are in the electronics lab and you have constructed a couple of circuits. And over these circuits, you have a current I1. Okay, so there is some non-zero current, that's enough. And then here we have another circuit where you have another current I2. The idea is that we know the following. Logically, if you want to summarize all what I'm going to say, I can say this. Because of this I1, I can find a magnetic field V1, which is a function of I1. And from this V1 as a function of I1, I can find a flux of the first circuit on the second circuit, which is equal to the V1 using PS2. Okay? This is all we want to say. Okay? So what do we understand from here? We understand the following. Or let me see if I can add more to this. Allow me to write this again. So this is equal, let's not forget this, that's D1. This was a function of I1, right? DS2. But this DS2 is a surface area element, which is going to be here. So, and this means that this flux because of the circuit 1 on the circuit 2, this is a flux 1, 2 is a function of I1. I think nobody can object to this, that this quantity depends on the current of the first circuit. So that's the general idea. Now let's try to describe this one. Okay, we have this loop, and the current is flowing in this way. And then using the right-hand rule here, this means that we have a current which moves around. It comes out like this, and it goes down like this. So it circulates in this way. So similarly, it comes out here, it closes down here, but at the same time, it comes out here, and it goes into here. Okay, so it goes everywhere. So this current here, it produces this magnetic field, which is in red. Okay? And now, this magnetic field that is in red is applying a flux, or we can measure a flux of this one on the surface area. So we can also calculate what is the flux of this magnetic field in some other area like this. But let's see what happens on this other circuit. So based on this one, we can say that this flux between these two quantities, this can be written as a constant L12 times I1. Okay? So for sure, we can write something like this. But now, a possible good question comes right now. Would you expect this flux, or let me ask it like this. Can you say anything whether this number L12, which is called the inductance between two circuit components, would this depend on the current? And the question I'm asking is this. We somehow, constructing a few arguments, we said that this flux In the end, it can be written as L12 times I1. Could this be also like this, L12 times I1 squared? So I'm assuming that we have a linear relationship between this flux and this current. Is this always true? Do you have any comment on this? So in these relationships, whenever we find whatever exercise we have solved so far, or examples that we have covered, have you ever seen a dependency of the magnetic field with respect to the square of the current?
No.
No, that's the answer. That's correct. So far, we've never seen the magnetic field to be mu0 I squared over 2 pi r or something. No, it's always linear, which means that this is a linear function. The b is a linear function of this, and at the same time, this flux is also a linear function of b. So it looks most probably this stands. So if the final flux is linear to I1, this means that anyone can draw a graph of the flux here as a function of the current here, I1. And this is going to be a constant value. And this L is the slope of this curve, which means that this current I, actually, this might even have to pass through the center. This is not passing through the center as I drew, if you look carefully, but it doesn't matter. But most probably should pass through the center, because if the current here is 0, the flux is also going to be 0. But if we keep increasing the currents, we keep increasing also the flux, which is expected. But overall, the slope is going to tell us how this mutual effect depends on this current. Okay, so this inductance is this quantity L12. Okay, and so this is, I think that the how can I say, the induction of an effect of this circuit or this one, I think everybody can accept this one. There's no question about this one. We're just trying to quantify their mutual relationship. And in order, the next question is the following: find L. Find what is the constant which constructs the linear relationship between the x and the y. So that's the next question. In order to answer this, we follow a couple of few steps, and these steps, they start like this. The first step, we have to determine a coordinate system. So we need to find a coordinate system, because we will need to integrate to find the flux. Okay, that's the first step, which is most of the time it's obvious. Even if you forget that this coordinate system is on the list, you don't have to worry much, because you have to do it because it's natural. The second step is that we assume that we have some current I. Okay, that's it. We assume some current I, and we include it in the equation. The third step is find B, which is a function of I. Okay, I could even include some words, find this, find that, but find B as a function of I. The fourth step is, it's also written over there so far. We need to find the flux of B, which means that as a function of B, which means that we need to find the flux as a function of B, which is also a function of the current, which means that this flux is also a function of the current. And we know that from the previous discussion, that this relationship here is a linear relationship. So after we do this, we have to calculate a quantity, which is called the flux linkage. So we denote it in our textbook. We use this notation. Many textbooks use this. And this is going to be equal to N times the flux, which is a function of I. Okay? This N is the number of loops. If this circuit here is composed of several loops, the flux, the effective flux that is affecting the whole system is multiplied N times. Okay, so this is what we need to do here. And finally, we can find this inductance, which is going to be the sixth step. And this inductance here is going to be equal to this flux linkage divided by the current. Okay? Because we said that it's a linear relationship. Okay. So this is the whole set of steps that we need to use. So, and then we can use this one for different configurations. Now, there are some super classical examples, and probably the example that we can select for this one is going to be the one that is also relatively intuitive, which is the following. Let's find what is the inductance between a circuit which has between a wire which has a current I1 and the circuit which has a width W, a length L, and it is at a distance of B. That's the question. Okay, so let's try to find out what is the inductance between these two systems. With system, we mean that wire and that specific closed wire loop. So then we look at the first step, coordinate system. Let's select what coordinate system would you choose in this case. Probably cylindrical could be a good choice. Cylindrical coordinate system. Then we assume a current I. Okay, we did this. The second question, and this is going to infinity. Okay, let's assume that this is going to infinity. What is the current here? And then here it comes a question that you asked me before a while. What are you going to use? Are you going to use the Gauss Law or an integral? Here, since this is extended to infinity, because of we can use the following. We can say B dl. This is equal to mu 0 I, depending on how much current we have here. If we had a different current, which is going to go like this, this would be I minus little I. Okay, but let's forget this for a moment. So, and also we can have also another current I little I2. This is again minus I1 minus I2. This is how we write this law, but I'm going to raise the ones in red pretty soon. And this is going to be BDL. This is the perimeter. This is going to be times 2 pi r. This is mu 0 r. So it looks like the magnetic field is equal to mu 0 I over 2 pi r. So it looks like the magnetic field is linear with respect to the current. We did this step also. Next step, find the flux, which means that this magnetic field, which is moving according to the right-hand rule, the current is going upwards, the magnetic field is circulating this way. This means that here, we're going to have some flux, and in order to integrate this one, it's good to integrate over some surface area element ds, over which the magnetic field is constant. Now, what is the union of the points where the magnetic field is constant? One can argue that this point here and this point here, they have the same magnetic field. But the magnetic field and this point, it's not the same. These two in red, they are the same, but they have different magnetic fields because the magnetic field is proportional to 1 over r. So further you get, it's going to decrease, but if the distance is the same, so r is this parameter. So it looks like for ds, we can select such a region which are equidistant. And this ds, we can write this one as L times dr. Okay? And then the flux has to be equal to the integral of b ds. And the b is equal to mu 0 I over 2 pi r times L dr. And we need to integrate this. And we have a lot of constants, which is mu 0 I over mu 0 IL over 2 pi r, sorry, 2 pi, and we have the integral of dr over r. What is the integral of dr over r?
ln r.
ln r. The limits, what are the limits? The limits are from d to d plus w. d plus w. So this is the flux. So it looks like we found this flux. The next step is that we need to find the flux linkage, which is n times the flux, and in this case is 2. I try to draw this one here like a couple of wires going on top of each other. So this means that by multiplying this by 2, I find this expression. So maybe, or let's also find the flux based on this expression here. This one we have calculated several times. So this is mu0 IL over 2 pi times ln of d plus w over d. d plus w over d. This was the flux. The flux linkage we multiply by 2, okay, which is going to cancel this 2 down here, but we keep it for the moment. And then we divide by the current, okay? So this is going to be our L. So it looks like we found it, because by multiplying with this 2, we covered step 5. By dividing by current here, we covered step 6, which are the last 2 steps. And finally, it looks like this inductance is equal to mu0 L over pi ln, so let's cancel this out so that we are not confused, d plus w over d. Okay, so this is all I wanted to say, at least for now, regarding the inductance. And I just want to go back and say once again that we have to assign a project, and today I'm going to send to you what the project is going to be. You just tell me by email the groups that you want to work, whether you want to work alone or in pairs. Do you have any question with what we covered today? If you don't have any, I can receive some more questions, but meanwhile we can stop the session. See you in the next